So that was our presentation. Thank you for that. No, just kidding. How many of you guys were at the NDC party last night? Quite a few. And you still made it here today. That's pretty impressive. When I woke up this morning, I sounded like Leonard Cohen, I think. My voice is a lot deeper today than it was yesterday. I think I got a little bit too excited during that concert, so that's a note for next time, not to sing along every song the evening before a talk. So what you just saw is our AI training to become a better driver. It's not really responsible driving, as you could see, but that's not what this is about either, because we're not really trying to compete with Tesla. This is more like better as in drive as quickly as possible to the finish line and don't let anything stand in your way. Now, we held this talk at JavaZone a couple of weeks ago, so this is basically the same talk. So if anyone was there, we totally understand if you want to watch something else instead, but if you found it so entertaining that you want to do another sitting, be our guest. No one left, that's pretty good. So around 2.5 years ago, there was this global event in the world, which essentially screwed everyone over, and continued to do so for the next 2 years. And it left the two of us with a lot more spare time in our daily life than usual. And we decided to spend some of this spare time collaborating on a fun project. And we'd previously done something similar before when we trained an AI to play a game called Pac-Man, or at least our own implementation of Pac-Man. But this time we wanted to do something different, something perhaps even more challenging, and we ended up with this native video game called TrackMania. How many have played TrackMania before? Heard about it, familiar with it, played it during class in high school? Most millennials probably did. I know you did.
Oh, yes.
So TrackMania, for those who don't know, it's a racing game. And as with most racing games, the objective is to drive as fast as possible to finish a track. It's a game that's been around for a while. And the latest edition was released in 2020, and that's the game that we've trained our AI in. Now, why did we choose TrackMania? First and foremost, we think it's a fun game. It's very visual. It's a good game, a good physics engine, and it's very fun to watch. And there's also a great community around the game. Other people who have worked with AIs, worked with similar problems, faced similar challenges, so there were people we could discuss problems with to figure things out quicker. And there are also useful third-party plugins available for extracting information from the game. On a more technical note, the game is deterministic. There's no randomness in the game, which means that if you execute a sequence of actions repeatedly, like you execute a sequence of actions and then you do it again, it will always produce the same outcome. So that makes it a little bit easier to train an AI to understand what's going on. Before we continue, let us tell you who we are.
Yes, my name is Malte. I work as a data scientist or data engineer, or what you would in Norwegian call a potato at Knowit. We have a stand out here, so you guys can come and talk to me after this talk if you guys want to, or ask any questions. I work as a consultant. I'm currently sitting at Entur, where we have a lot of fun with data from the public transportation sector.
My name is Manu. I'm from Oslo. I've been working as a developer consultant for 5 years. And prior to this, I was doing my master's at NTNU in Trondheim and at UCSB in California, where I specialized in AI. And that's where I developed this interest, and it's an interest that I've held on to later, obviously. And currently, I'm working at a Norwegian consultancy company called Above It, where I work as a developer, but I'm also a part of company management. And it's very easy for people to mistake Above It for other companies with similar names. And that's especially when we introduce ourselves at the same time, it's often done. But above it is a totally separate company, but it's pretty new, so a lot of people haven't heard about it. But it's a consultancy company. And as a consultant, I'm currently outsourced to the public transportation company called Ruter. So if you took the bus today and the screen was showing like the totally wrong information, that may or may not have been my fault. But you know, I've been here for 3 days, you know, so probably my fault. So we're going to show you more videos, and we're also going to talk about implementation. But before we get to all of that, I want to do the compulsory recap on artificial intelligence, just to make sure that we're all on the same page. AI is a very broad topic, but simply put, it's about simulating human acts of intelligence in machines. And then you have machine learning, which is a subcategory of AI, where data is used to train models to solve problems. Additionally, the algorithms used in machine learning, they're very general. They're not explicitly programmed to solve a single problem. For example, neural networks, what they learn is primarily dependent on the data that is fed to them. So theoretically speaking, and this is very simply put, but you can solve any problem using machine learning as long as the data sufficiently describes the problem, and there is a pattern that can be discovered for finding a solution. Now, there are many different types of machine learning, or there are a few different types, like main categories. You have supervised learning, you have unsupervised learning, and then you have reinforcement learning, which is what we used to train our AI. And reinforcement learning sort of stands out because the data that is used for training is created by the model itself during training. While these other methods, they use data sets that you compose beforehand. Reinforcement learning is particularly suitable for training AI in games, because instead of handcrafting how you want the AI to act in a game, or even by providing examples, you just reward the AI for preferred behavior, and it will learn the optimal way of playing by itself. And this is also why game AIs can produce moves that even human experts wouldn't think of, which has happened in the last few years in games such as chess and Go, where very advanced AIs have been developed, and they have surpassed human performance as well. And you might be thinking, yeah, but these are just games, right? But they're like solving these problems are being used as games are being used as stepping stones for solving harder problems in the real world. You have different methods and variations in reinforcement learning as well, because you have different algorithms for learning and etc. But there is a general algorithm, and to understand how it works, I need to introduce a few terms. So you have the agent, which is the entity that is being trained. So in TrackMania, you can say that the car is the agent. And then the agent can pick an action from a set of possible actions. So when you play the game on the computer, you use the arrow keys to accelerate, brake, you steer to the left, to the right, and also there are combinations of these as well, because you can accelerate and steer right at the same time, right? And then the environment is the world which the agent can interact with. So in terms of TrackMania, the environment is basically the entire game itself. It's a container for the environment. It's the platform which is used. A state is a snapshot of the current situation that the agent finds itself in relation to obstacles, possibly adversaries, or anything else that the environment might consist of. So what you see here is one particular state, and just a few moments later, you're in a different state, or the agent is in a different state. And between these two states, you can see that the car has moved, but the car doesn't really have to move for the state to change, because even if the car isn't moving, the environment is still alive. So it's more correct to say that that state is a function of time. As time progresses, the state also changes. Last term, the reward. When an agent performs an action in a state, the environment provides a feedback which is used to measure the degree of success or failure of that particular decision. And rewards can be both positive and negative, so that's why we'll call negative rewards for punishments. And unlike actions, which they're defined by the game itself, what you can and can't do, right? But how state and rewards are represented, that's really a design decision, because the game doesn't really tell you how to do that directly. It's your job as a programmer or as a machine learning engineer. So in this situation, you see that the car is going to crash into a wall, which is not a desirable behavior, so you might want to punish the agent for doing so, and that you have to program in as well. So how does all of this fit together? Well, you have the AI, or the agent, which are terms that we'll use interchangeably. Then you have the environment. The agent picks an action in the environment, and then the environment will return the next state that the agent finds itself in, and also a reward. And the AI will take this information and use it, run it in the chosen learning algorithm in order to learn from its experience. So if it is a positive reward, then the AI might choose to perform the same action again the next time. But if it's a negative reward, then maybe it's better to try and avoid that action when it finds itself in a similar situation. And during training, the agent goes through this loop for many, many iterations until it gets to a point where most of the time it will choose actions that lead to positive reward more often than negative. So to summarize, reinforcement learning, it's about maximizing the total amount of reward in the long run, or in a session, or while playing a track, right? It's like training a dog to do tricks. So while we were working on this, we used mostly Python for programming. And then we also used a language called AngelScript, which is sort of similar to C or C++. I say that like if C and C++ are identical, which I wouldn't know because I'm a Java programmer. But anyway, AngelScript is a game-oriented language, which is used to extend the functionality of games. And we used it to create a plugin of our own to get more information out of the game. We also used a library called Stable Baselines 3, which is implemented using PyTorch by Facebook, or Meta, or whatever they're called now. And Stable Baselines 3 consists of already implemented reinforcement learning algorithms. It's kind of like how scikit-learn is for general machine learning, or how OpenCV is for computer vision. It's a library that consists of implemented and optimized and ready to go out of the box reinforcement learning algorithms so that you don't really have to implement those yourselves. And from this library, we use something called the Deep Q network. Not going to go into how it works and all that, but if you're familiar with Q-learning, which is a traditional RL algorithm, this is like Q-learning with neural networks. We also used something called proximal policy optimization, PPO. It's a method that was introduced by OpenAI a few years back, and at the time, it performed so well that it became the go-to reinforcement learning algorithm because it performed better than other state-of-the-art methods.
All right.
Here you go, sir.
Thank you. Thank you for talking about all the boring things.
Yep.
Let's talk about some fun things.
No worries. Anytime.
All right, so let's talk a little bit about the training process itself. The AI was trained on my stationary computer at home. It's a Windows computer it was built in 2017. So starting to get a little bit old. I have a GTX 1080 Ti, if anyone cares about that. So the game, TrackMania, was running on one process on my computer, and then the AI was running on a different process. And the way they kind of communicated, if we can call it that, is that the agent just simulated key presses as if a human being is pressing arrow keys on the keyboard, and then the game would act accordingly. And the agent was implemented in a custom OpenAI gym environment. And for those of you who don't know what that is, you can think of it as an interface for reinforcement learning algorithms. So we would have stable baselines who has implemented the PPO or DQN algorithm. And then it would interact with our environment, and the loop would go as Manu has explained. This was also streamed, partially at least, to my Twitch channel. If anyone want to watch some fun TrackMania training, twitch.tv/Kamlasa. It's not actually training right now. I probably should have started when I'm thinking about it, but we'll probably start very soon. Yeah, all right. So we did this project in kind of 4 phases. And what we mean about that is that we started with only the necessities for training, and then we added more complexity and features along the way. So in the first phase, we only used a screenshot of the game as input. So the AI is only taking the screenshot into consideration. And then we added speed and turning angle as well. So now it knows about the screenshot and the speed and the turning angle. And then we actually started out with the PPO algorithm, but then in phase 3 we changed it to the DQN. And then we added some form of crash detections to see if the car is crashing into the walls. And then the 4th phase, we started hooking into the game API through a TrackMania framework called OpenPlanet. All right, so during training, the AI trains in first person, like in this screenshot. And if you look at the top middle, you can see the speed. It's 0 right now. And in the top right, you can see the distance. But the AI cannot see these. The AI only sees the screenshot, not the speed and the distance. And what we want to do is to have something like this. This is the goal, the end goal, to train an AI. And what we have is that we have the state in the top left corner here. But the screenshot, or the state, or the screenshot, the same thing. It's really just a long array of numbers, like raw pixel values. And we want to feed this to some kind of a black box that we call it, or a neural network. And then we want the neural network to tell us what actions that we should pick. And this is achieved doing something like this during training, like Manu already has mentioned a little bit. We have the state, we feed it into a neural network. The network tells us what action to pick. The environment then feeds back a reward or some kind of feedback to the AI. And if it's a good reward, hopefully the AI will learn that in this certain state, we should probably do the same action more. But if it's a bad reward, we should probably try another action in the same state next time. And this then continues, this loop continues for hundreds of thousands of iterations until the AI hopefully learns something. We also do a little bit of image processing before we feed it to a neural network, because if you just feed it like a raw HD picture, that's a lot of pixels, that's a long array of numbers. So what we do is that we cut this image in half horizontally. So we remove a lot of... Okay, Siri, I like that too. So we cut it in half horizontally because the top half doesn't really give us any useful information. In this project, we actually don't care about the cloud. And then we also use inverse binary thresholding, so we would turn it black and white. And then it's going to look something like this. But there's still quite a lot of pixels that we have to work with, so we resize it into something smaller. And now we have something that we can actually feed to a neural network. Also a little bit about how we do the rewards. When you do reinforcement learning, the reward engineering is also really important. And what we do is that we give a reward based on speed, so the faster the car drives, the more reward it gets. And also we look at the final track time, or like the finish time of the agent. And the faster the track time is, the better reward the agent will get. And then we also give some kind of punishment or negative reward. If it gets stuck, that also means we need some kind of detection for when the AI actually gets stuck. And the way we do that is simply by looking at the speed. And if the speed is less than 10 for about 5 to 6 seconds, we just assume that the agent is stuck. And we just reset, make the AI start over and give it some kind of punishment. Also, if the agent uses over 1,000 time steps, or about 50 to 55 seconds of driving, we also just assume that it's never gonna reach the finish line. And so we also just start over and give it some kind of negative reward. All right, so let's look at some videos. This is the training in phase 1. It's also really important to note that when in reinforcement learning, when you start training, the AI doesn't know anything about the game or physics or anything. So it just performs kind of random actions. And you can try to notice in the speed in the top middle, it barely reaches 100, and that's because it only does random actions. So let's see if this works. Yes, it does.
It's driving better than you, though.
Yeah. I'm actually quite unhappy showing exactly this example because it drives way too well. It actually comes into, almost manages to finish the first turn. Usually it just drives into the wall and just stops and starts over. But yeah, this is at the very beginning, just doing random things. And this one is about 10 hours into training. And you can again try to notice the speed in the top middle. It has learned how to accelerate, but it doesn't really handle turns so well. So it kind of just rides the walls into the finish.
I meant it's driving better than you in real life.
Well, yeah, for sure. You don't want me to drive. That's for sure. Yeah. So eventually, it reaches the finish line just before it was about to reset. So that's quite fortunate, I guess. 49 seconds, about 10 hours in, and then after about 20 hours of training, it is actually going to hug the right side of the wall because now it has learned to accelerate and turn right at all times. Yeah. It almost gets stuck, but barely manages to escape.
Maybe explain why it turns just right.
I will try to explain it in. I got a question if I can explain why it always turns right, and I'm going to try to explain it in 1 minute. First. It's 42 seconds, so it's learning. It's driving faster. So let's try to take a look at some highlights of the best runs from phase 1. Yeah, they drive in about 40 seconds, all of them. Now the sound is working, that's nice. Yeah, so it finishes in about 40 seconds, all of these. And yeah.
Has a pleasant sound.
Love that scraping of metal sound, yes. All right. So at this point, we also discovered that we had a bug, and it is that the car would never brake because I mapped it to the wrong key on the keyboard when it simulates key presses, so it actually never brakes. So we can pretend that the reason why it's always driving right is to not crash into the wall and get stuck, but it's actually slowing down by always turning right and just rides into the finish. We can pretend that that's the AI is that smart. We don't know though, that's just a theory. All right, so 40 seconds, it's not that great. I drive it in about 18 seconds, is decent time on this track. So why is reinforcement learning so hard? Well, number one is that, as I mentioned, the agent always starts from scratch when you train in reinforcement learning. We have the credit assignment and reward shaping problem, and that's how you make your rewards. It's actually quite difficult. We have the exploration versus exploitation trade-off problem, where you want to explore the state space, but at the same time you want to exploit a good strategy. And then reinforcement learning is also really sample inefficient. It takes a long time to train. So how many here play board games? I would assume quite a few. Yeah, okay, that was quite a few. Right, so when you guys learn how to play new board games, you wouldn't just do random moves, right, and see what happens. You would like read the rules and understand the game at a higher level of abstraction, right? But that's not what the AI does. The AI just simply starts out and tries to learn the environment by doing random things. And that's a reason why it takes so long for a reinforcement learning agent to learn. And why do we compare to humans? Well, we are the benchmark for now. We are the best at generalizing. Humans, we generalize a lot. When we start to learn something new, we actually have a lot of experience doing similar things, usually. And we perform the best, and we learn the fastest. So the credit assignment problem is that when an agent gets feedback, it's quite hard for the agent to know if it got feedback, or if the feedback, it's hard to know if the previous action was good, or if it was a previous action that was performed in 100,000 time steps before even, if that was the action that was good, right? So for instance, in TrackMania, it's hard for the AI to know if it drove, let's say the AI sets a new personal best on this track. It's hard for the AI to know if it drove really well in the beginning of the track, or if it drove actually really well in the later stages. For it to learn that, it has to drive the track over and over again. And then they have the reward shaping problem. And it is how you engineer your rewards. There's kind of two ways of doing it. The number one is called the uniform assignment scheme. And when you do something like this, you only care about the result or the final product of whatever you're trying to achieve. So for instance, in our case, we would only care about the track time. We would only give it feedback when it finishes the track, and based on, and of course, the faster it drives, the better the feedback would be, right? And the really positive thing about this is that the AI or the agent would get really, really sophisticated, because we would tell it that we don't care how you do it, you can exploit bugs, you can cheat, you can do whatever, we only want you to finish as fast as possible. But that also means that for a long period of time, when it's driving in the track, it's not going to get any interaction from the environment. And therefore, it converges really slowly. The other thing that we can do is use something called shaped rewards, and that's what we're using in this project, right? We're micromanaging a lot more. So you give it rewards for driving faster, give it rewards for not crashing, punished for getting stuck, punished for taking too long, and stuff like that. And it converges a lot faster because it gets input from the environment all the time, but it doesn't get as smart because we're micromanaging too much. And then we have the exploration versus exploitation trade-off. And when you train reinforcement learning agent, you want to try to explore the state space, right? you would want to try to explore the entire state space, and maybe you even want to perform every action in every state, even multiple times maybe. And if you could do that, honestly, you could just make like a huge Excel spreadsheet. You could just have like, okay, we're in this state, you know, we have state in one column, and then we could have the action in another column. And then you could just, when you're getting a new state, you could just look at this spreadsheet and be like, okay, we're in this state, we're going to perform this action because it has done the best previously. But the state space in TrackMania is obviously too big to do something like that. So what you want to do then is try to exploit a good strategy when you think you have found one. And this is often just implemented as every time the agent picks an action, there's a small chance that it's going to perform a random action instead of actually choosing what it thinks is the best. So for instance, when you saw the AI drive just now, when it hugs the right side of the wall, there's a small, every time it picks an action, there's a small chance it's going to do something random. So eventually it's going to choose to drive to the left, and when it drives to the left, it's hopefully going to accelerate faster and learn that that's maybe a better way of doing it, and therefore it can exploit that strategy instead. Yes, and the last one is that the last problem why, or the last reason why reinforcement learning is so hard is that it's really sample inefficient. So this graph shows the amount of time it takes an agent to learn a game called Frostbite. And on the y-axis, we have the Frostbite score, and on the x-axis, we have the amount of hours trained. And you can see the humans are doing really well. We get above 4,000, about 2 hours of play. But the agents, DQN agents, they need to train for hundreds of hours to even almost reach that level. All right, so let's talk about phase 2. As I mentioned, we added speed and turning angle to the state, which we think is really going to help the agent to learn faster and better. And then we also had a bunch of technical improvements, I'll call it. You know, we fixed the bug where now the car can actually brake. It's quite important. Yeah, and then just to try to explain why it matters so much that the AI knows the speed. If we take this screenshot, for instance, in this screenshot, it turns to the left, further ahead. And if the agent knows that the speed is 0, it should probably choose to accelerate, right? But if the agent knows that the speed is 400, in order not to crash, it should maybe start braking a little bit. So knowing this extra information is actually going to influence how the AI behaves. All right, so let's take a look at phase 2. Okay, and let's look a little bit more in depth of some driving. So here, it doesn't hug the right side of the wall anymore, so that's quite nice. It has also went from about 40 seconds down to 30 seconds, so actually a 10-second improvement, which we're really happy to see. It's still crashing quite a lot, but it is definitely performing a lot better. So we're really happy how much it improved in phase 2. All right. It's your turn again.
Mm-hmm. Thank you. So as Malte was saying, we tried to progressively improve the set of features that we used to represent state in order to improve the performance of the AI, but also to reduce the training time. And he's been going through all these things now that worked out well, but there were also things that we tried out that seemed promising to begin with, and then it turned a little bit more challenging, and then in the end it wasn't really that viable. So I'm going to talk about the stuff that didn't work, but we did try some interesting approaches, so it's worth talking about. So up until now, we've been feeding the AI raw pixel data from screenshots of images from the game, and also then we added the speed and the steering or turning angle. But now we wanted to try and specialize the features even further. As you could see, the agent was crashing a lot into the walls, so we wanted to address this by perhaps try and measure the distance to the walls from the AI's point of view, because maybe this will be useful information for not crashing into the wall anymore. So this is kind of like drawing lines from the middle of the screen towards the wall, and then you measure the length in pixels. To do this, you first have to find the walls. And we gave it a go using tools from OpenCV, computer vision tools. We started out by using canny edge detection, which is, as you can see, an edge detection algorithm. And it also removes noise from the image, given a certain threshold, because as you can see, it doesn't really care about the edges on the road, and doesn't give a shit about the cloud. I'm not sure if I'm allowed to swear, but now I did. Sorry, NDC organizer people. And then, as Malte also showed you earlier, we cut out the top half of the image because we don't care about what's going on there. We only care about the road and the walls. And then now we need to determine if these edges are lines. Now, what's the difference between an edge and a line? There is a distinct difference, but I'm not going to explain it to you now. but what you need to know is that we need to find lines. And that we do with something called Huff line transformation. Both of these methods are just used out of the box using OpenCV, so we didn't really implement anything here for using those. Now we have all these lines, but we don't need all those lines. We need 2 lines, one for each wall, to know where the wall begins, where it ends. So through interpolation of these lines, we can approximate a line for each wall which covers the length of the wall. And then we can just draw out lines from different angles from the middle, and then we hit the walls. So the interpolation isn't perfect, but it's pretty decent, a good starting point. Does anyone see a problem with this approach of measuring distance?
The perspective is different, because if you're straight ahead, you need a longer line to represent the same distance.
Exactly. So there's a problem with perspective here, as you said. Because this is a 2-dimensional image, and we're trying to measure distance in a 3-dimensional space, which doesn't really make sense. So I want to use a laser pointer, but I think it's a little bit too packed for me to go out there and shoot at the screen, and the overflow streaming people are going to be mad at me for not showing them the same thing I'm going to show you. So I'm going to see if I can get an arrow out here. Do you see an arrow moving around? Well, that sucks. Okay, so I'm just gonna head out here. We're gonna use this screen. Sorry, streaming people, you should have been down here. So if you look at this point, and then you look at this point, do you guys see over there? Yeah, good. This point is actually further away from a game perspective than this point, but this line is actually shorter than this line, which doesn't really make sense. And this isn't always the case either, because sometimes it's intuitive and correct, but that means that we got an inconsistency problem as well, so this information isn't really going to be useful. And I was a little annoyed by myself for not seeing this beforehand, before implementing this, because it's kind of obvious, really. But anyway, we didn't really want to scrap this momentarily, so we want to add some information and see if we could make it useful anyway. So we decided to partially start over. What we want to do now is to identify the entire area of the wall, and more specifically, the height of the wall at the point where those arrows that we drew out hits the wall. Because as you can see, like the middle arrow, that small arrow in the middle, the wall is shorter there than on the right side, right? So the closer the wall is, the taller it's going to be as well. So this could be useful for making this information viable. So first we turn the image grayscale, and now you can see that the wall is a lot blacker than the rest of the image. So in the next step, when we use something called inverse binary thresholding, the wall which was black now turns white, and all the brighter pixels turn black. So this is a similar method to what Malte was showing earlier, but it's like an inverse. And this is useful in the next step when we want to identify the contours of the wall, or both walls. And this is also just a method out of the box, didn't implement anything, just used OpenCV. And now we have all these contours, many different, they look like they're interconnected, but they're actually different sets of contours all along the walls. And each contour consists of a set of points. In the next step, we take all of these points, we use a clustering algorithm called dbScan, and then we identify the two largest clusters, assuming that those are going to be the walls in the image. And now we just have these points, but we want a shape of each wall. So we used a library called AlphaShape and computed a concave hull for both sets of points, and then it looks like this. So a concave hull of a set of points, that means find a shape that encloses all of those points in the set. And as you can see, it does a pretty good job. It's not perfect, but it's actually a lot better than what I showed you earlier. And the lines that we now draw out are a lot better, except the one in the middle, which is completely useless. But now we get like a perfect hit on the wall. And we can also measure the height of the walls at those points. Now the problem, because there's a problem here as well, is that, I mean, this looks very promising, but there's a lot of complex algorithms and expensive computations being done here. I mean, we basically over-engineered the whole thing with dbScan, concave hull, blah, blah, blah. So when we tried to use this during training, it just wasn't fast enough. So we ended up just scrapping the whole thing, didn't use any of it. And that was a couple of months of work. Ended up going for a simpler solution for crash detection that Malte is going to talk about in a bit. You get to talk about all the stuff that worked.
Yeah, because I made them. Nah, it's just a joke, guys. All right, let's talk a little bit about phase 3. So we changed from PPO to DQN. Even though that PPO is better on paper, me and Manu, we understand DQN a lot better, so it's easier to like debug and understand the behavior of the agent. And then we did add some crash detection. And so you can just forget about all those fancy words Manu was talking about. And the way we actually ended up doing it is, remember we had this image from when we did some processing of the raw pixels from the screenshot. What we ended up doing is that we, in the same way, we just took from the bottom middle of the screen, we just drew lines until the first black pixel, because the white is just completely, the road is completely white, and the wall is the first black pixel that it hits. And then we measured the distance here as well. And I think it was, if the distance is less than 420, then it's actually crashing. And it works quite well, actually. So I don't, perspective. I don't know what that is, but this is for where this worked good enough,
You
Yeah.
want to fight?
Yeah, no. All right, so with some crash detection, we can then punish the car for crashing. So let's see how that influenced the AI in phase 3. Let's take a look at some highlights. Yeah. All right. So it is actually driving quite a lot better than phase 2 even. We can take a look at some closer looks here. And the track time now went down from about 30 to about 20.5 seconds of the best ones, which is almost at the level I'm at. I was driving it at around 18. So we're quite happy with how this is going. We're just adding more stuff, and it's going quite well. And then we go into phase 4, going for the Holy Grail, getting pumped up. And what should also be noted is that until this point, we actually have done it, the training, similarly to how a human would train. We only looked at the screen and only simulated key presses. That was also one of the premises for this project. But now we were thinking, if we want to do it even better, maybe we should just hook into the game API to get some even more precise stuff and more data. And what the API gives us is really only 2 things. It gives us a way to detect when the countdown has ended. If you guys have noticed, before the car starts driving, there's the 3, 2, 1, go. And until now, the car or the agent has really just been trying to drive while that countdown is going, which means that it's trying to perform actions, but it doesn't get any feedback, so it just creates false data for us. And this data is then trained on later. Similarly, it gives us a way to detect when the car crosses the finish line, because until now, in TrackMania, when you cross the finish line, it takes like 2 or 3 seconds before this menu pops up. That's really easy to detect, but before that, it's quite hard. So when it crosses the finish line, it also tries to drive for like 2 or 3 more seconds and also just generates the wrong data for us. But the API fixes this problem, which we thought would actually influence it quite a lot. And the way we set it up was that we set up a socket server and a client. So we had the game running in one process, and then we had the socket server. And the game would just continuously send these kind of data to the socket server, and then the agent would pull the data from the socket server. So there's a small delay, but it's almost negligible. Yeah, so let's see how phase 4 went. So that's how that went. What it actually need to know is that when on the starting block in TrackMania, there's no walls around it behind the car. So the car actually learned to drive down on the grass. There's this huge grass area around the track that it can just drive freely. And the reason it did this, we think, is that we have too high reward for just driving fast. So it would just drive down on the grass, and it would just drive back and forth for 50 seconds until it restarted, of course. Yeah, so we have too high reward for that, and then on the grass as well, it would never crash. So it doesn't get any punishment for crashing. Yeah, that's what we think at least. So we don't know, but yeah, we'll continue working on this after phase 4, and yeah, maybe we'll see you next year at NDC, guys. All right, thanks.